So it's my pleasure to introduce you again for your continuation of your mini course. And, please take it away.
Okay, thank you. So, Andrei, please give me your guidance if I'm going in too many details over some subjects. So let me remind you what happened previously. So we want to consider a certain two category based upon cotangent bundle to Lie algebra GLN with the adjoint action of the group GLN. And on general principles, an object there would be a variety Z with the action of GLN, and also a superpotential, a function on Z cross Lie algebra, which is invariant with respect to that group action. So any pair would define an object. And geometrically, this would correspond to a fibration over certain Lagrangian subvariety inside a cotangent bundle to Lie algebra. So cotangent bundle is symplectic, and a function over the base, so a function over the base of cotangent bundle determines a Lagrangian in the bundle, the graph of its differential. And variety Z serves as the space for auxiliary parameters, as they're called in classical mechanics. So let me just remind you, that in a very pedestrian way, moment is partial derivative of W with respect to the corresponding coordinate, and derivatives with respect to auxiliary parameters must be equal to 0. So this determines Lagrangian base, and over that base, certain pieces of Z may hang, figuratively speaking. These equations may leave some coordinates in Z unrestricted. So the morphisms between two such objects naively would be coherent sheaves over the intersection of these fibrations. But precisely this is the category of matrix factorizations of the difference between superpotentials over the common base G. See, this is common, and then you also have these auxiliary parameters from both objects. The category of matrix factorizations is supported very close to the critical locus of W2 minus W1. So this critical locus corresponds to the intersection of these to the product of fibers over the intersection of these Lagrangian subvarieties. So we're following intuition, but with precision when it comes to computing exact category. Now, in this category, there are some special objects. A special object has Z as a symplectic variety. So again, generally Z doesn't have to be symplectic to determine an object. But let's assume that Z is symplectic. It has a Hamiltonian action of G. And then there is a moment map from Z to Lie algebra, to the dual of Lie algebra. I confuse here Lie algebra with its dual. I assume they're identified by Killing form. So W is the trace of X. Sorry, just a moment. So here we have X, which belongs to the base Lie algebra, and mu is a map from symplectic Z to the dual of Lie algebra. So this is a special object. By the way, what would be category of morphisms between two such special objects. It will be something special. If you write it out, you get matrix factorizations over the product of these two symplectic varieties cross the Lie algebra. And you have to take the difference of superpotentials, which will be trace of Lie algebra matrix X times the difference of the between moment maps. If you apply Koszul duality, if you trade X, which is even, for an odd set of variables, for an odd matrix. I'm sorry. This computer is really, just a moment. Behaves in the, okay, now it's normal. Sometimes it does wild things.
It senses when you're worried, so then it misbehaves.
Okay, yeah, maybe. So you apply this Koszul duality and you trade G for odd variables, odd counterpart of Lie algebra, and the superpotential is traded for the differential. And the differential will be Koszul differential, which sets the difference of moments to 0 in a derived fashion. So as a result, you get this, you get coherent sheaves over the symplectic reduction of the product of these two symplectic varieties. So again, I remind you that Z1 and Z2 are assumed now to be symplectic varieties with Hamiltonian action of G. And so home between their objects is just combined, is the reduction of their product. So it's a very special thing. So the object that we use for braids to represent affine braids is of this special type. It's cotangent bundle to the flag variety. So very explicitly, you parameterize cotangent bundle by a group element, which tells you how the flag is oriented up to Borel, and a nilpotent matrix, which is in the cotangent fiber. So this is up to action of Borel. And the moment map is conjugation of this matrix Y. So the category of endomorphisms would be category of matrix factorizations, G equivariant. So you have two flag variety, sorry. So you have two flag varieties and Lie algebra, so a lot of coordinates. X times the difference between momenta. Now, you see, so you can use G equivariance to put the first flag in the standard position. Then X times the first moment would pair the red triangles. It would pair the upper part of Y1, which is the whole Y1, with the lower triangular part of X. That's what the trace of X mu1 does, pairs them up. And so by Knorr periodicity, you can throw away both. So Y1 is completely gone. And what remains of X is upper triangular matrix. So X becomes Borel, Y1 is gone, and G equivariance is traded for Borel equivariance because you put the first flag in the standard position. So now you have two Borels. The group element, so the first flag is standard, the second flag is parameterized by the group element G here. You're left with the second, you're left with the second matrix Y2, which I simply call Y now, and with the Borel matrix X and a rather simple superpotential. That's the W. So X is upper triangular, Y is strictly upper triangular. Now, if you apply Koszul duality to, so you see the superpotential is linear in both X and Y. So you can apply Koszul duality to either X, traded for odd variables, or to Y. So if you apply Koszul duality to X, this tells you that Y, conjugated Y has to respect the standard flag, and ultimately you will get coherent sheaves over derived Steinberg variety. It is derived because you trade W for differential, and you cannot get rid of the differential completely in this case. Or if you trade Y for odd variables, then the differential will say that upper triangular X must also respect the rotated flag. So then you get Grafendiek Steinberg, which is a matrix, GLN matrix, and two flags that it respects. There is no need to derive. So you get categories which were previously used by Bezrukavnikov and Bezrukavnikov-Risch for constructing categorical action of the braid group. Again, from their point of view, it's not easy to see that Steinberg or Grafendiek Steinberg will give you two equivalent representations of the braid group. This equivalence is of a fairly derived nature. It's not something, you might think that this is very similar. In one case, it's general, and in the other case, it's nilpotent, but this relation is very non-trivial. If you derive them both from this matrix factorization description, maybe you can see a little bit better why they both are the same. Okay, so we have this homomorphism from affine braids into the category of endomorphisms of our special object. Identity braid here will be represented by Koszul matrix factorization of this superpotential. Now, I remind you the idea of Koszul. If your superpotential is a sum of products of polynomials, then the matrix factorization, easy choice, would be tensor product of algebra, one way you map by Pi, the other way you map by Qi. So that's what the Koszul matrix factorization is. And if Pi's form regular sequence, then the choice of Qi's for representing W do not matter. So it is sufficient to tell you what Pi's are. So to represent identity braid, your Pi's are strictly lower triangular entries of the matrix G, the position of the second flag. If you kill the lower triangular entries, then your second flag also becomes standard up to Borel. And the superpotential becomes zero if the red triangle is zero, because you conjugate strictly upper triangular Y, it remains strictly upper triangular, so its trace with triangular is zero. So, and these matrix elements form regular sequence, so we just write the corresponding matrix factorization. That's the identity braid. That's the easy one. And there is another set of easy matrix factorizations which correspond to Eustace-Murphy or Bernstein-Lustig special, actually Andrei loves them. These are special elements in special affine braids, which correspond to moving a strand around the inner hole or outer hole, it doesn't matter. So you put the points of the braid, you arrange them radially, as in this picture, and then you take one of these points and move it along its own circle around the hole. And that's the element in the affine braid. It has a very simple representation. You take the identity braid that we just described, and you tensor multiply it by one-dimensional representation of the left Borel or the right Borel equivariance groups. I remind you that our matrix factorization category is equivariant with respect to the product of two Borels. Now, since in identity braid, you reduced the group G to Borel subgroup, you killed all the lower triangular elements of G, then, so homologically speaking, G, the group, is reduced to Borel. You have two Borels acting on the left and on the right. So this Borel makes them equal to each other. So it doesn't matter whether you choose left or right one-dimensional representation of the corresponding Borel. So it's one of these which reflect the action of diagonal element of the Borel subgroup.
But this is if you think about the coherent sheaf on like a product of two flag variety or symplectic reduction of two flag varieties. One of them, one is the diagonal and the other just a line bundle, right? Is that
yeah, so this is
corresponding to a character of Borel.
Yeah, this is line bundle over flag variety. That's what it just tensoring with one of these canonical line bundles, the quotients, or maybe they're duals. So there's some technicalities which I don't remember right now, but can be restored. So this construction has a horizontal structure, which is important for topologists, maybe not so important for algebraic geometers, for Bezrukavnikov and Drish, who studied it. So we represented the affine braid, sent it into endomorphisms of this object FL. Now, you can put one affine braid inside the other in a canonical way. Here is the picture. So affine braid has a hole inside it, and into that hole you can put another affine braid. Now, here we even have a Lagrangian correspondence between two categories corresponding to GLN1, G times GLN2, and GLN1 plus N2. Sorry, so let me say it differently. What I want from this horizontal structure is to match it by the structure, by the corresponding functor between the categories in which we send affine braids. So I want to explain that there is a functor from endomorphisms of, here it is. I want to explain this functor, which sends endomorphisms of N1 cross endomorphisms of N2 into endomorphisms of N1 plus N2. But in fact, you have even more. You have a two functor between a product of two categories of GLN1, GLN2, and GLN1 plus N2. And again, the choice here is fairly, one could easily guess what it would be. So what I have to construct a Lagrangian correspondence between the product of cotangent bundles and the cotangent bundle. So what is the choice of that Lagrangian correspondence? It will be again described by auxiliary coordinates and superpotential. So this Lagrangian correspondence is a special object, I should say it explicitly. Here it says that it is a special object. So all the most canonical things in this construction are all special objects, and again, it's not a coincidence. So if I have time at some point, I will comment why they're so special, because it all comes from the upper floor. So we need a symplectic variety with the action of GLN1, GLN2, and GLN1 plus N2. All of these actions have to commute, and this will then give us that special object. So we take GLN1 plus N2 and take quotient by the subgroup of the matrices that I indicated here in green. So they're identity and identity in N1 by N1 and 2 by N2, anything in the upper right corner and 0 in the lower left corner. And the corresponding quotient has a name which Alexei mentioned last time. I don't remember, sorry, what the, did he say steel variety? Steel manifold? There was a simple name, I'm sorry. So take cotangent bundle to it. So the quotient itself has the action of all three groups, GL N1 plus N2 acts on the left. And you can see that GL N1 cross GL N2 normalize this subgroup H, so they act on the right. What this variety is, let me say it in a pedestrian way. It's a Grossmanian. Of, let's see, N1 inside N1 plus N2, if I'm correct, equipped with a basis in N1 and in the quotient of the total space by the subspace. So it's a framed Grossmanian. That's what it is. So it defines a Lagrangian correspondence. And it's an exercise to see that it turns, so it will turn the object FL N1 cross FL N2 into FL N1 plus N2. That's an exercise. That it will combine two flags sitting in these. It's very natural. A Grossmanian equipped with framings, you put one flag into the subspace, you put the other flag into the quotient, and it combines them into one big flag. That's what it does. And moreover, and therefore, it will also provide a functor between endomorphism categories. So technically, it looks like this. You have matrices X and Y, which are block upper triangular, and you have matrix G, which is block diagonal. So first of all, you perform a pullback. So you allow matrices X and Y to have upper right matrix elements. They will not enter in the superpotential. And also you allow matrix G to have upper right entries arbitrarily. They will not enter in W. So it's a very easy pullback. And after that, you have to push forward to allow matrix G to have lower triangular elements. And this is done with the help of Kazul. So you write Kazul matrix factorization for matrix elements in the red lower left rectangle. In other words, you write differentials which shoot by these elements one way, and the other way you shoot by whatever you need to compensate for the difference in superpotential created by the fact that now you can rotate more. So this gives you extra terms in W, which are killed when red is 0. So you can present them. So they are in the ideal generated by this red square. So you can write the bilinear presentation and write Kazul matrix factorization. So we end up with intertwining the products of affine braids into total affine braid. Everything looks nice. Okay, so let us now switch gear a little bit. So what I said before can be done without matrix factorizations. And I'm very, should be honest about this. So you will not surprise Roman or any of his collaborators with this story. They can do it in an odd way. They will not see the commuting variety in their story, but they will see all the categories that show up here and all the structure. Okay, so now we add framing. So commuting variety was this. Oh, sorry. Just a moment. So this quiver represents commuting variety, and this quiver represents general moduli space of instantons. So what is it? You know it better than I what to do. So first of all, you multiply your GLN Lie algebra by a space, I called it VRN. It's a space of dimension R times N. These are homes from framing space into our CN.
It's like exchanging the roles of epsilons and delta in calculus. It will confuse everybody. In everybody, so in Nakajima theory, we call it W, that space, the framing space.
W?
Oh. V is the space in which the group acts, and the space which you anyway. You don't have to change it now, but in the future, I think it's yeah, that's Nakajima would call it W exactly. Thank you.
He also calls vectors I and J.
That is true, yeah.
Well, there were even worse choices in history, I think. Sorry. Okay, sorry. So the tricky part is that you have to impose stability conditions before you take the symplectic quotient. Namely, you have to say, so V is an element from this home space. So you can apply V to vectors of CR, and then you can apply powers of X and Y to V. We do not assume that they commute yet. And this should generate the whole CN. So there shouldn't be a sub-representation. I'm saying it in a very pedestrian way, in a very technical way, that you should generate the whole CN in this way. If not for a stability condition, this would be another standard story about cotangent bundle that can be told in the derived geometry language, where you trade cotangent bundle for odd tangent bundle. So you trade matrix factorizations for Koszul resolutions, so to say, whose differentials, whose odd parts come from this odd tangent bundle. That's the source of Koszul resolutions. So the object, but we impose the stability condition, and we had previously discussed how this affects the two category, so we can handle it, cutting out the non-stable part of this cotangent bundle. So the objects that we consider here are exactly the same as in the previous story. So you still need a variety Z with the action of G, and your W now may also depend on the vector V from the space W. So this is this VNR, which is also known as W. VNR, also known as, sorry. But we will use the same main object. So it's still cotangent bundle to flag variety and same W. So we do not use the framing vector here. We could, but we don't use it. So we could play with it a little bit, but we didn't play yet. Just independent, which is good because in case when R is equal to 1, if I'm correct, Nakajima explains that stability together with the commutativity will tell you that covector is 0. And here it's also 0 because the superpotential, so our Lagrangian subvariety defined by this superpotential will have the covector equal to 0 because W does not depend on it. So partial derivative is 0, so our W is 0, the one from home from CN to CR. So therefore, our Lagrangian will fit with stability, will lie nicely in the quotient of the stable subspace of cotangent bundle. Okay, so the endomorphism of our object now is the following. So we take two cotangent bundles to flag varieties as previously, a copy of Lie algebra, also now vectors, framing vectors, V and R, which is your W, and the old superpotential, and I forgot to close the bracket here. And we have to impose the stability condition, which I indicated in green. So the stability, so there will be two stability conditions. Recall our discussion. We have to say that V, the vector acting on the vectors from CR, together with X, which is directly matrix from Lie algebra, we have it, and the moment map as it comes from both from both auxiliary varieties should generate the whole CN. So here we have, generally speaking, two stability conditions, one for the first cotangent to flag and the other for the second. But as I mentioned previously, they coincide on critical locus. So therefore you can drop one of them and still get the correct category, equivalent category. So you can use either both or just one. Which means that I can still do Knorr. So if I do not impose the stability condition on Y1 and X, and only on Y2 and X, then my Y1 is unrestricted, and I can do Knorr, and I can kill the lower triangular part of X by this Y1. I can do this Knorr, which reduces X to Borel and gets rid of one Y. So we can still end up with a close relative of our short category for braids, which would be G, group G, which tells you where the second flag is. The first flag is standard. Nilpotent matrices for parametrizing cotangent fiber over that flag. Borel matrices, that's what's left of X. And the framing vector and the stability condition, which is written here explicitly. Note that on the critical locus, so X is upper triangular, that's given. It's Borel subalgebra. Y, adjoint of Y is not strictly upper triangular, because Y is strictly upper triangular, but when you conjugate it by group element, it doesn't have to. But on critical locus, it is strictly upper triangular. So the part of adjoint Y, which is not upper triangular, this piece, is homologically trivial. So when it comes to formulating stability, we can ignore it. So therefore, this vector V, I call it vector, it's a map from CR to CN. So let me remind you that this guy is a map from CR to CN, that's who it is. Must have the lower row to be non-zero. So at least one entry in the red row must be non-zero. Because if the whole red row is zero, then X and Y will never be able to bring it up to the upper rows. So you will never be able to generate your CN. You will generate only, you will not generate the subspaces corresponding to the subspaces of the standard flag. At least not on critical locus. So therefore, this red row, one of them must be non-zero. And this has two corollaries. Well, before I mention the corollaries, here is what it means. consider a Kazul complex. So L0 is trivial one-dimensional representation of, I'll be playing with the metric factorization for the identity braid. So for me, left Borel action and right Borel action are equated by the fact that the flags are, the second flag is also standard, so it's parameterized by Borel. So it doesn't matter whether I use left Borel or right Borel, I can translate one into the other. So I consider Kazul complex, which is a product of complexes killing each of these red entries of the matrix V. From the Borel point of view, you shoot from the trivial representation to each of the one-dimensional representations of Borel, to the nth one-dimensional representation of Borel. That's what you do. Because these are the weights of the lower row. They all have the same weights with respect to Borel. So you take tensor product, and since it's a standard argument, since one of these V's must be non-zero, always, it means that this complex is contractible. So if R is equal to 1, if we're in the Hilbert scheme realm, if we're talking about U1 instantons, this means that L0 is homotopic to Ln, because they form a contractible cone. So you get this. And when you tensor it with identity braid, you get a complex between identity braid. Should put here a hat. So 1 over a hat over 1 means matrix factorization corresponding to identity braid is the same as the matrix factorization of the nth usus Murphy, which means that our homomorphism from affine braids into the category factors through ordinary braids. So we get this. We get representation of the ordinary braid group. This is a missing part of the previous story. So as far as I understand, when people wanted to represent ordinary braids, they would use D-modules rather than coherent sheaves. So they would use a quantization of this story. Again, that's a separate story. In fact, the whole 2 category can be quantized in this case. The 2 category of cotangent bundle to Lie algebra can be quantized or deformed. So, but if you do quantization, then you would have to map ordinary into affine and then into endomorphism. So it will be different. So here, the homomorphism of affine braids factors through the ordinary braids. In other words, you plug the hole in affine braids by introducing a one-dimensional framing, which matches physics string theory expectations. So this I may explain later if you want a little bit of strings thrown in the mix. So we're very proud of this fact. And it's funny that introducing framing has the same effect as quantization. I think one needs maybe quantized 2 category of Hilbert scheme is equivalent, maybe the category of Hilbert scheme is equivalent to quantized 2 category of cotangent to quantized commuting variety. That's a conjecture. I don't know if it's true, but I bet some money on it. Okay, if R is more than 1, so if we have genuine instantons, then we will play Andrei's game to get something interesting. So let's introduce extra equivariance acting on the framing space CR. I think most appropriate thing would be to put there a flag and so get a Borel equivariance. Here I put a C star, but I think better would be Borel. Here it doesn't matter. Then this contractible Koszul complex, K theoretically would mean a relation between the classes of these Eustace-Murphy elements in the braid. So the nth Eustace-Murphy in K theory would satisfy this relation, which means that at the level of K theory, a fine Hecke will factor fruit cyclotomic Hecke, and we'll go into the K theory of the K group of this category FL, of endomorphisms of the flag variety. So we conjecture that the latter arrow is an isomorphism, that this is categorification of cyclotomic Hecke, but at least we can say that there is a homomorphism from cyclotomic Hecke to fine. From cyclotomic Hecke to K theory of this category. So this construction, I think it was expected for a long time that cyclotomic Hecke is related to instantons, R being the degree of the polynomial, of the cyclotomic polynomial. And in fact, this is how it shows up naturally here. Okay, so the case R equal to 1, the case of Hilbert scheme, gives us a little bit more. We can get link invariance out of this construction, which was the whole purpose, in fact. Denote by V and the fundamental representation of Borel, or GLN. We will need it in a moment. So we proved two theorems. The second one is in progress. Alexei writes it up. So the first theorem says that, again, here is a little bit of cheating in this formula. So I don't want to dwell upon it, just a little bit of technical cheating. Consider Holmes from identity braid into the matrix factorization corresponding to braid beta, tensor the sum of exterior powers of the fundamental representation of GLN. So you see, since we're working with equivariant categories of matrix factorizations, almost the same as coherent sheaves, we can easily tensor with representations of the equivariance group, which is the advantage of this construction, makes it easy. So theorem says that what you get is an invariant of the closure link of that braid. So take that braid, close it in a cyclic circular manner. That's the picture, how you close it. And the space home will not depend on the choice of representation of the link as a closure of a braid. There are many different representations, but they will all give you the same space home. This space will have three gradings. The Q grading, which scaled X and Y in the opposite ways. The T grading, which was scaling just Y and also was of homological nature. And the grading corresponding to K, the exterior power of V that you throw in the formula. So this invariant categorifies, I should add here, sorry, should have said that. Just a moment. Okay. This space, triply graded space. categorifies, which means it's graded Euler characteristic matches, categorifies the Homfley PT polynomial of the closure link.
Question.
Yes.
So you said that one of the grading insights is it's the same as the covariant and homological.
Yes.
Is it really a theorem or is it expected? Because kind of parallel results with coherent shapes are usually pretty difficult to prove. It's like that's kind of purity of X and so forth.
I'm sorry, say it again.
So in the coherent shapes world, it sometimes happens that if you have like X between two objects, whatever say case X between objects is actually has the case homological grading, but also is scaled by a particular monomial in a covariant variable. I mean, some kind of purity result. That's usually pretty difficult to prove for coherent shapes. Is that for you? Is that somehow automatic, or it's
I wish
the fact that some homological grading is exactly equal to covariant grading? That's
that homological grading is equal to what?
You're saying that some grading is equivalently either homological or covariant.
No, sorry. It's okay. Let me say a little bit more. So first of all, T grading is a combined grading. It combines the scaling of Y, of the cotangent fiber, and whatever homological shift I would need. So the cotangent bundle has weight 2, so it's even. But when I write matrix factorization, the differential will have grading 1. So I have to shift the modules, the free modules in matrix factorization to make sure that the differential has degree 1. So this T combines. That's number 1. Number 2, in this category, there is a family of objects. Maybe should call them Kazhdan-Lustig objects. Again, I don't know what's the proper name. Such that homes between them, surprisingly, exist only in 0 T grading. So,
yeah, was exactly my question. Is that a theorem or is that an expectation?
It's an expectation and a theorem which we're writing up with Alexei. So in all this is yet another categorification of fine-Hecke and Hecke. So then you expect to see special objects, which in topology we call flat graphs. They're not braids, but there's something interesting topologically. They represent flat graphs. And homes between these flat graphs should exist only in 0 T degree. And it's also true here. So we have here, when I introduced matrix factorizations for braid on 2 strands, in that case, we had W, which factored into 3 factors. And so there are 3 ways to arrange for a Koszul matrix factorization, depending on how you split 3 into 2 plus 1. And one of them corresponded to identity braid. The second corresponded to positive elementary or negative elementary, depending on extra shift with respect to Borel. And the third object was this first example of non-trivial Kazhdan-Lustig object. And so we prove that homes between these Kazhdan-Lustig elements indeed exist only in trivial T degree, which is, I may comment a little bit on it.
And what sort of argument goes into proof of that?
Unfortunately, we use a rather technical argument. We're untying these flat braids. So some people used that before, that there are certain relations between these objects which allow you to untie. So, sorry, these objects are constructed by composition of elementary ones. So you get a braid-like structure, except that it's not a braid, it's a graph. And then there are technical ways to untie these flat graphs, closed braid-like flat graphs, in a way similar to how you would untie a braid, a closed braid. There are similar moves. And then you reduce everything to a knots whose homology you can compute directly and see that it exists only when t is equal to 0, at 0 t degree. So this is a natural proof. More interestingly, what is so special about these objects? So again, I'm not an expert in the previous 30 or 40 years of Kazhdan-Lustig. Apparently, they were constructing them sort of by hand. So here, these special objects are almost Chern characters of objects which live one floor above. So again, I didn't talk about these objects yet, except I mentioned it in passing when we talked about two-strand braid. So these are special matrix factorizations here. And they, I mentioned that this category, let me say it. So our category endomorphism of FLN is almost a center of a free category. This is some twice categorified Riemann-Roch, which explains why such a relation. You see, this endomorphism of FLN is almost coherent sheaves over Steinberg variety. And Steinberg variety is a Hamiltonian reduction of a cotangent bundle. So it didn't have to be that way. So it's a very special category. Now, in that free category, there are some objects, natural objects in the free category. So you can send them down to this endomorphism of FLN, and they will become Kazhdan-Lustig objects. So as far as I see it, the special feature of Kazhdan-Lustig elements is that they're Chern characters of someone or images of K theoretically. There's some things that come from free category. Now, what does it mean? It means that when you compute Holmes between them, it's like computing, there is a statement that if you have a symplectic variety and two Lagrangian subvarieties there, then X between them, the statement I think has to be corrected by square roots of canonical bundles. So up to some details, Holmes between two Lagrangian subvarieties is the same as Hochschild homology of their intersection. So you take their intersection and consider usual cohomology there. So the same applies here. So when you compute Holmes between these two objects, all you have to do is intersect corresponding Lagrangian subvarieties, and you will get, the intersection will look like Grassmannians, like a bunch of flag varieties. And the cohomology there sits on the diagonal of the Hodge diamond. So this is what is involved in this miracle. The intersection is, these are special objects. Holmes between them are isomorphic to cohomology of intersection of corresponding Lagrangian subvarieties. The intersection looks like a bunch of flag varieties. Bott-Samuelson variety, that's what it looks like. I have to think a little bit to be more precise. And when you compute cohomology of that, you see that everything sits on the diagonal of Hodge diamond. And this is the miracle of t degree being 0 in Holmes between them. So it's not a very complete explanation for the miracle, but at least it's something. I think there are other miraculous things involved, but I do not understand it yet. So I do not have a very clean explanation why it exists only in t equal to 0, but at least I know what is special about these objects. They're Chern characters of someone living one floor above. Did it make any sense?
It made perfect sense to me, except I'm a little bit worried about your allusion to things being like flag varieties. Usually, if you can start dig deeper, that sort of purity is some kind of, again, some kind of purity statement. And usually, if you go deeper and deeper into GLM, that gets harder and harder. But maybe there's some, maybe I just don't understand. Maybe there's some divergence between the theory, between the two theories. So maybe it is true that your cardinalistic stuff is somehow always survives, and you can always deal with. I mean, you can always deal with just Grassmannian flag varieties. But.
So if I remember correctly, if you compute homes between these objects in this category and FL, it will be reduced to computing cohomology of Bott-Samuelson variety. So this fact has a natural explanation.
Cool, super.
And then you have to explain why Bott-Samuelson resides on the diagonal of the diamond.
No, Bott-Samuelson is a nice variety that you can see. You can really see its cohomology is pure, so it's not.
So again,
let's continue.
Okay, sorry. So it's for me, it bothers me. I thought I could have a direct explanation. I said that to Losev, and then I couldn't produce, so I think I lost his respect after that. Okay, so that's theorem 1, that we get link homology out of this braid representation. And theorem 2 in progress is that this link homology is the same as the one derived from Zergel bimodules by standard construction. So we can explain how to get from this representation to Zergel representation. So in fact, with Zergel-Rukia, so in fact, we prove that there is a functor from the category NFL to the category, to the homotopy category of complexes of Zergel bimodules. I don't want to go there because I don't think, maybe you're not so much interested in Zergel stuff, but I could comment more about how this works. It is a natural construction. It's not something very fancy. There is a natural way to go there. But there is some, again, unexplained miracles and coincidences. So this requires a separate story. So let me comment a little bit on the proof of theorem 1. Why closure, why taking home with identity braid? Actually, it's not home, it's Tor rather. So I'm cheating a little bit. It's rather a symmetric thing. Home is not symmetric, Tor is symmetric. So why does it produce invariant? It turns out it's not too hard to prove. So there is Markov theorem, which says that if the same link is constructed by closure of two different braids, then these braids may be related by sequence of moves of two types. So the first type of the move is that if you use braid, which is a product of two braids, then you can switch the order for obvious reasons. Now, proving our invariance with respect to this move is very easy, because again, this is Tor, so everything is symmetric. This is an easy stuff. The trouble is with the second Markov move. Here I show you the picture, what the second Markov move says. Take braid beta, add to it an extra strand, which does not participate in the braid, and then cross it with the nth strand of beta. That's the green square where this crossing happens. You can use positive crossing or negative crossing. Then your link will be the same as the closure of beta, because you get this extra loop which you can untie. So if you're with a little bit of experience in 3D topology, you recognize it very quickly, that this loop can be removed. So it turns out that this construction, actually as well as Zergel, behaves differently with respect to positive and negative crossing. So it's straight invariant when you do the positive crossing, and it involves a shift in the third degree. You have to add these powers of Vn to establish invariance with respect to the second move. So there is some funny stuff for this invariance, which says that what we construct is more naturally an invariant of transverse links rather than ordinary links, but nevertheless can be tweaked into the invariant of ordinary links. So how does one see this invariance, that you can remove this extra loop? So I'll comment just a little bit. So first of all, the funny thing, so good news is that you have to check this M2 only on one side of the braid. I never appreciated this fact before. So you would think, what's the difference, checking it on the right or on the left? But in the realm of Hilbert's scheme, this makes a huge difference. So how would you compute home from identity braid to a braid in this category? So here is a reminder what the category is. So you have group element, Y matrix, X matrix, and a framing vector with the stability condition and this superpotential. So one can see that taking home with identity braid means that you restrict the group element G to Borel. So you simply restrict your matrix factorization to Borel subvariety inside G, which kills your superpotential immediately. So there it's equal to 0. So now your matrix factorization turns into B square equivariant coherent sheaf. You still have to impose stability. Then you use one of the two Borel equivariances to unwind the Borel group here. So you remove this Borel by using, let's say, the second Borel. So now you lost your Borel subgroup in the variety, and you also lost one of Borel equivariances. So now you have to take the product of strictly upper triangular matrices, and framing space, impose stability condition, and take the quotient by Borel. And it is a smooth variety, surprisingly, because you see, I never imposed a condition of commutativity. In this whole story, commutativity never showed up, which is good. So what is this variety? Again, it's an easy exercise, a triple of strictly upper triangular, a vector, and they have to generate the whole space, and you take quotient. It's very easy to see. I cheat a little bit. I ignore the diagonal entries of the Borel matrix. They don't play much role. So suppose that both matrices are strictly upper triangular, no difference. So what you get is an iterated bundle whose fibers are projective spaces of increasing dimension. So your first base is a point, P0, and then you fiber P1 over it, which means you get P1, and then you fiber P2 over it. It should be something canonical. I don't know what it is. Maybe someone will recognize, just compute this and recognize what these varieties are. It must be something known in algebraic geometry. So the point is that closing the last strand, the nth strand, the site is important, can be done by simply pushing forward along the last fiber. So you have to take sections over the last PN. And luckily, the complexes involved in the matrix factorization of the braid, which looks like this, arbitrary beta plus an extra crossing with the nth strand. These complexes have no sections or homology over Pn. Pn has a desert from O-1 to O minus n plus 1, there is a desert of line bundles which have nothing. And these are the ones that, sorry, where am I? Sorry, oops, just a moment, lost my way. Here. Here. So in the complex corresponding to that special braid, the bundles over Pn mostly live in the desert, except for one, which is O0. So it has exactly one section, and the rest has no sections. So this crossing doesn't, so you can compute this push forward explicitly and see that all you get is the closure of the braid beta. So that's the technical side of the proof. See that closing that extra strand means pushing along that last fiber, and use the fact that there is a desert. So you don't need to know the complexes because those spaces will have no sections. Okay, so we have horizontal structure here, similar to affine braids. We can put ordinary braid inside a fine braid and get a bigger ordinary braid, which is done again by Lagrangian correspondence. But this time framing is present. So again, this Lagrangian correspondence is based on this framed Grassmannian and some extra piece, which is needed to impose the following condition. You have a framing, let's just consider r equal to 1, since that's what we do mostly. So you have framing vector in Cn1 plus N2. But you have this intertwining Grassmannian, so you can send that framing into the quotient by the N1 dimensional subspace. So now you impose an extra condition that the image of the framing vector from N1 plus N2 should equal the framing vector in N2. So it matters on which side you insert the ordinary braid in the well, the side matters here. So this extra Cn2 is required to write it as this condition as a superpotential. But the condition again is just saying that the framings agree. You can map you can send big framing from the big space into the smaller space in the Grassmannian, the quotient space. And this corresponds to the idea that when you do pullback on matrices X and Y to combine N1 strands and N2 strands, you want to impose stability condition eventually. So you do not want to impose stability condition, you do not want pre-existing stability condition in the upper left square. Because ultimately you do not know which part of this big rectangle, the upper rectangle, will give you stability. It may come from this generation thing may come from upper left square, or it may come from upper right rectangle. So you do not want to commit yourself to stability in the upper left square. So you simply say no stability condition there. You need stability in the lower right square, either in big one or in small one. That's the same. You still have to bring because your big stability vector sits in the lowest row. So you have to bring it up somehow. So you bring it N2 levels up by the lower right. So that one must satisfy stability. But when you bring it to the upper levels, you don't know which part of the matrix does it. So you keep it uncommitted, you keep it affine, no stability condition. Which means, by the way, that we cannot easily put two ordinary braids side by side. In the Zergel construction, that's the easy thing, putting two ordinary braids side by side, combining them. But here, this operation doesn't work. At least I don't know how to do it. So this is the end of the technical story about braid representation. Now, my plan is to show you pictures. So it's a picturesque part of the talk. So can I talk for another 15 minutes or so?
Of course, yes, especially if it's with pictures. Yeah.
Now there will be pictures that physicists like. Mathematicians, people categorifying quantum groups like this type of pictures. So you will see them in Kavanagh-Lauda and related family of papers, and people categorifying Heisenberg. So the point here is to explain why our constructions should lead ultimately to even double categorification of Heisenberg, or categorification of Heisenberg with of GL1 with two tildes, and how this is all related to links and braids. What's the relation there? So everything will be in one picture eventually. Conjectural to a large part, but nevertheless, I think it's true. So the story is that if you have an n-dimensional topological quantum field theory, then there is a big story related to Lurie, which I do not know. So I'm telling you a very pedestrian story, which I learned from David Nadler over lunch. So the manifolds that show up in the story will have two types of boundaries. Or rather, their boundary will have two components, slightly intersecting. The genuine boundary and the cut boundaries. So the cut boundaries for gluing. So you can glue only over cut boundaries, but then there are also genuine boundaries over which you're not supposed to glue. So if you have a k-dimensional manifold, which has no cut boundary, then to it,
sorry, Lev. Are they supposed to be with corners, or what does it mean? You have two boundaries intersecting.
Yes, I think this is what people might call corners. So there will be pictures, so you will see corners. I think. Okay. Maybe, again, I'm not sure. I learned it from. Okay, but I think it is with corners. So I'm giving you a very pedestrian version. So if there is no cut boundary, then to a k-dimensional manifold, you associate something I call mk hat, and that's n minus k minus 1 category, whatever that might mean. So -1 category is just complex numbers, no objects, no morphisms, and 0 category is a vector space. So they're objects, but no morphisms. Otherwise, if your manifold has a cut boundary, then it represents an object in the category of its cut boundary. And if you glue two manifolds of the same dimension over their common cut boundary, then you get an object which is home. Then what you get is the category, or a number, again, depending on where it happens, a category, which is home between their objects in the category of their common cut boundary. So now I will start showing you pictures, and this will start making sense. So I want to do it first before we get to a 3D. So our story corresponds to 3D to QFT. So dimension will be 3. I refer often to something one floor above. So that will be 4-dimensional TQFT used by Kapustin-Witten to explain Langlands. That's our neighbor on the upper floor. But in this story, we have 3D. But I want to first explain how I understand a 2D version. a topological quantum field theory, which is called B model, and it's based on a family of Calabi-Yau varieties. Is that okay for?
In what sense? Of course, it's okay. I mean, everything.
Maybe you heard it 100 times, and one of my colleagues at some, well, okay, I shouldn't. When people hear this story, this story is not very rigorous, at least the way I will be ignoring orientations, which is bad, to make it shorter. But when people hear the same story 10 times, they start getting angry. So please tell me. Okay.
Gelfand used to say you have to hear something 12 times before you understand. So.
Okay. So here is the local pictures. It's a two-dimensional theory. So space-time is two-dimensional. It's a piece of a surface. And this surface is, on this surface, we have lines, black lines, which may intersect at points. You may even have a point sitting on a line. In fact, you can have a point, even a point sitting all by itself. That's also, oops. Oh my God. Sorry. Just a moment. You can have a point which is just all by itself. What is this? This is a flat, two-dimensional, smooth CW complex. So in topology, you learn what is a CW complex. So the idea, I guess, is to avoid smoothness and to concentrate on continuity. But here we consider a smooth version. So you have one cell, 0 cells, 1 cells, 2 cells. That's, I think, the proper way of thinking about this. This is also known, especially in a non-flat case, it would be called a fold, but let's ignore it for now. So the regions are colored by these Calabi-Yau varieties, and the lines separating them are colored by sheaves or complexes of sheaves on the products of these varieties. And how to color dots, we will see in a moment. So implementing the previous suggestion to a point, a green point is just a point that you choose in one of these domains, in one of these 2 cells. So for example, here. So to a point, you should associate a category, namely coherent sheaves over the variety in which domain this point resides. If you have 2 points, maybe in different domains, or could be the same, or 2 cells, to that you associate a category of their product. Now, if you have a one-dimensional manifold whose boundary is a point, and it ends at this black mark, then this should correspond to an object in the category of X. So the black mark should be colored by the sheaf, by a sheaf from sitting on X in accordance with the theory. If you have a segment which connects points X1 and X2 with a mark in between, this creates an object in the, should create an object which is a sheaf over the product. So that's how you should mark the, that's how you should color the black mark. If you glue 2 segments of the above type at point X, now I'm talking about this situation. If you glue them together, then again, by general rule, this segment with 2 black marks should correspond to the vector space, which is home from E to F in the category of sheaves over X. At this point, you can ignore the green point X. So you can say that this is just the same as simply having 2 black marks and a line connecting them. Next, you may wonder, what if you have two black marks sitting on a line and x2 being in between? Then you should compose, you should do the convolution of the sheaves E and F, meaning pull back, tensor product, push forward, the usual stuff, and you will get a sheaf on x1 cross x3. So here we should, this means, pictorially, this means you have one point, you have another point, and instead of one black mark between them, you have two black marks called E and F. So to figure this, you introduce a green point in between. In other words, you cut this segment into two by the middle green point, and then you use the argument. If you have a circle with three black marks, for example, here, then, well, there are equivalent ways to cut it. So you can cut it at x1, and so first of all, let's cut it at x1 and x3 by these two green points. So we cut it here and here. So now we have two one-dimensional manifolds whose boundary is these two green points. One is F mark, this is sheaf F, and the other is a convolution of E1 and E2. So to this green circle, one should associate the space of humps between E1, E2, and F. Of course, again, the picture looks symmetric. My definition looks not quite symmetric. That's because I'm ignoring orientations. So therefore, if in your two-dimensional picture you see three black lines intersecting at a point, this black point in the middle, zero cell, you wonder, how should you color this zero cell? You look at its link, meaning this green circle. You look at the space represented by this green circle, which we just described. And so by general rule, the disk inside that green circle should represent an object of that green circle. So a vector in the vector space of that green circle. So the point X must be colored by a home by a vector from that above space. So the point is that when you color every point in the original picture, according to this rule, then you should be able to associate a vector to any green circle containing many points, many singular points inside. And if in your picture, if your picture is compact and outside you have a trivial variety consisting of a single point, which would be just a trivial variety, then to this whole thing you will be able to associate a number. Now, question, what should one associate to just to a circle, which lies completely in the domain color, in the two cell colored by X? So the idea is to put two green points on that circle. In other words, to cut it into two semicircles. Each semicircle is an object in the sheaves over X squared, X cross X. But the condition of composition, this convolution story here about E and F, tells us, you see, if you compose, well, let me write it here. Why should I make a very specific choice for this green segment without marks? Because if I compose this one with any mark on it, that should be the same as equal, maybe not the right sign, maybe better to say homotopic. Equivalent in the right sense to this. So here we have x1, let's say x1, and here generally x2, and here just x1 and x2, same E. So this means that this segment from x to x should correspond to identity functor from sheaves over x to sheaves over x. This sheaf over the product represents a functor from category of sheaves over x to categories of sheaves over x. So it should be identity, so it should be structure sheaf over the diagonal because of that relation that we want to maintain. So if we wonder what to associate to a circle, we glue together two arcs, each is a diagonal. So we're supposed to take the endomorphism of diagonal in the cross product of two x's. So it must be Hochschild co-homology or co-homology. Again, have to pay attention to orientation to make that choice. Let me ignore this. Of the category of coherent sheaves over X, which is just, let's say, differential forms over X, or multi, how do you call them? Multi-vector fields, depending on whether it's homology or cohomology. So in particular, so let me just, if may I speak for another 3 minutes to end with a little bang, if that's okay. So in particular, if you have a disk filling this green circle, to that you should associate identity in this Hochschild cohomology. It's an algebra naturally, because it's, for example, because it's category of endomorphisms of an object, so it has monoidal structure. So to this you should associate identity in this endomorphism. So let me finish with these pictures. Riemann rock light in the category of coherent sheaves. Consider the following picture. It's an annulus. It has an outer boundary. So the whole annulus is colored by variety X. On the boundary you have sheaf E, and there is a marked point where you have an endomorphism of E. So this marked point is just endomorphism of E. And then you have inner circle. So what you see is a two-dimensional manifold with a cut boundary. So it should define a vector in the space corresponding to inner green circle. So the corresponding vector is called Chern character. Again, here I'm cutting some corners because there is square root of a roof hanging around. So Chern character from the B model physicist point of view is the vector created on the green circle by this annulus. Now, if you have a disk which is colored by X, you have sheaf E on the side of the disk, and you have endomorphism F on the boundary. To this, you should associate a number, because on the outside there is nothing, or just X, which is 1 point, trivial X. And there are two ways to compute this number, depending on how you want to cut the disk. The first way is to cut it along the green circle. So from the outside, you get Chern character. From the inside, you get this identity, which we saw here. The vector space of a circle has a natural pairing. So you apply this pairing, and you get your number. All vector spaces come with pairing in this story. Or you could cut your disk into two half disks by the segment. To the segment, you associate a category of endomorphisms of E. So then to upper half disk, you associate identity endomorphism. To lower half disk, you associate F on the nose. And you take, so both represent vectors in the space of endomorphisms of E, Again, there is a pairing, so you apply that pairing. So left should be equal to right. In other words, if you want to know the Euler characteristic of sections of a bundle, you can just integrate its Chern character. The actual Riemann rock is when you do a similar calculation with an annulus, which has two black boundaries, two circles. You can cut it over the middle green circle, or you can cut it radially, then check what you get. That's the actual Riemann rock. Okay, so what I want to explain, if I have a chance, next week is how these same pictures apply to our story with Alexei. So instead of categories, we'll have two categories. So to green segments and green circles, we'll be associating categories. The domains will be, the two cells will be colored by instanton moduli spaces. We'll fix, for example, fix R and play with the number of instantons. And the black lines which separate instanton domains will be, surprise, surprise, the edges of Nakajima quiver somehow. So that's what I want to explain next week, if possible, that edges of Nakajima quiver represent homes or functors between two categories associated to Nakajima varieties of another quiver. So you can combine these two quivers in this way. Okay, and I'll stop here.
Super. Questions? Maybe I'll start with a technical question. Same day, same time. Is that good for you next week?
Yes, absolutely.
But guess it's we can also ask for audience input from that. And other questions? All right. Maybe I was just so super clear that everybody. Well, last call for questions. If not, let's thank Lev. Was for a very inspiring talk, and we look forward to more, to three-dimensional version of these pictures in exactly 1 week. Thanks so much.
Thank you, Andrei. Andrei, may I ask you a quick question?
Sure. Yes, of course. Yeah.
Maybe an inappropriate one. So you previously had a talk by Yakov Kononov.